In 1953, British railway engineers arrived at the workshops of South African railways with notebooks in hand and cameras ready. They weren't there to offer advice, they were there to learn. For decades, Britain had taught the world how to build locomotives, but now, deep in the semi-desert of the Karoo, a machine was running that defied everything London's engineers thought they knew about steam power. It could haul 1,000 tons across waterless wastes without stopping. It recycled its own exhaust. And Britain wanted it desperately enough to send teams halfway around the world to figure out how the hell it worked. The locomotive they came to study was South African Railways Class 25, and it represented something the British Empire couldn't stomach. A colonial railway had out-engineered the mother country. The Karoo is not kind to machines. Stretching across South Africa's interior, it's a landscape of stone and thorn scrub, where temperatures swing 40 degrees between noon and midnight. Summer days crack past 110 Fahrenheit. Rain, when it comes at all, evaporates before it reaches the ground. Rivers marked on maps flow maybe once a year. For a steam locomotive, which drinks thousands of gallons of water daily, the Karoo was a death sentence. By the late 1940s, South African railways faced a crisis. Freight traffic was exploding as mining and agriculture boomed, but the routes crossing the Karoo had no water. Every 20 miles, trains had to stop at condensing stations where steam was laboriously turned back into water and pumped into tanks. It was slow, it was expensive, and it couldn't scale. The Cape Government Railways had tried everything: water pipelines that cracked in the heat, underground cisterns that ran dry, even proposals to haul water by train to supply other trains. Nothing worked. Then an engineer named L.C. Grubb asked a different question. What if the locomotive didn't need external water at all? Condensing locomotives weren't new. They'd been tried in Russia, in Egypt, in the American Southwest. Every version had the same problem. The condensing equipment was so heavy and complex that it strangled the locomotive's power. You saved water, but lost performance. The trade-off wasn't worth it. Most railways abandoned the idea entirely. Grubb thought he could solve it. Working with designer A.G. Watson at the Salt River Workshops in Cape Town, he sketched a locomotive that would condense nearly all its exhaust steam back into water while maintaining the pulling power of a conventional engine. The key was a massive condensing tender, essentially a mobile cooling plant on wheels, that would roll behind the locomotive like a shadow. In 1953, the first Class 25 emerged from the workshops. It was a 4/8 four-wheel arrangement, massive by any standard, with a boiler pressure of 225 pounds per square inch, and cylinders driving wheels nearly 6 feet in diameter. But the real engineering sat behind it. The condensing tender was a cathedral of steel and copper, fans 8 feet across, thousands of cooling elements, way ducting that snaked through the structure like arteries, and a water tank holding 9,000 gallons. The entire tender weighed 112 tons when loaded. Here's how it worked. Exhaust steam from the cylinders, instead of blasting out the smokestack, was diverted into the tender. Fans, powered by a small steam turbine, forced air across banks of cooling elements where the steam condensed back into water. That water, now purified by distillation, flowed back into the locomotive's tanks. The system could recycle up to 90% of the water used. A Class 25 could run 700 miles across the Karoo without taking on fresh water. The British heard about this and didn't believe it. Steam locomotives were Britain's gift to the world. From rocket to flying Scotsman, British engineering had defined what a locomotive should be. In the idea that a colonial railway, operating in what many British engineers still dismissively called the bush, had created something London couldn't match, was professionally offensive. So they sent a delegation. Engineers from British railways and private firms arrived in South Africa with a simple mission: figure out if the Class 25 was real, and if so, how to copy it. What they found shocked them. The Class 25 wasn't a prototype or an experiment. It was in regular service, hauling freight trains up the grades between Beaufort West and DR, working shifts that would cripple a conventional locomotive. Test data showed thermal efficiency levels. British steam engineers hadn't seen outside theoretical papers. The condensing system worked. It worked brilliantly. British Railways decided they needed this technology immediately. Back in London, the plans were drafted for a British condensing locomotive. It would use the Class 25's principles, but scaled for British conditions: smaller, lighter, optimized for shorter runs with tighter curves. The project was classified urgent. Britain's railways were hemorrhaging money, and coal costs were rising. A locomotive that recycled its water could also recycle heat, improving fuel efficiency by 15 to 20%. But there was a problem. The Class 25 wasn't just clever engineering. It was brutally expensive engineering. Each condensing tender cost more than 2 conventional locomotives. The cooling elements required copper and specialized alloys that were in short supply post-war. The fans needed constant maintenance. The ducting had to be cleaned regularly, or efficiency plummeted. Worst of all, the system only made economic sense in places like the Karoo, where water was so scarce that the alternative was not running trains at all. In Britain, water was everywhere. Every valley had a stream. Every town had a standpipe. The economic case for spending double the cost to save water that was abundant made no sense. The fuel savings were real, but they couldn't justify the capital expense. The British condensing locomotive project died in committee meetings and budget reviews. Not a single unit was built. Meanwhile, in South Africa, the Class 25 kept running. 50 locomotives were built between 1953 and 1955. They became the backbone of Karoo freight service, moving wool, minerals, and agricultural products across routes where no other locomotive could operate economically. When crews learned their quirks, how the fans needed to be throttled carefully, how the condensing system could ice up on winter nights if you weren't careful, how the whole machine had to be treated like the precision instrument it was. The Class 25 had one more trick that impressed the British. It was fast. With 6-foot driving wheels and a design optimized for sustained running, it could hit 60 miles per hour on flat track while hauling a full load. Conventional wisdom said condensing locomotives were slow plodders, sacrificing speed for water savings. The Class 25 proved you could have both, but by the late 1950s, the same force that had killed Britain's condensing project was coming for South Africa's: diesel. Diesel-electric locomotives didn't need water. They didn't need the elaborate maintenance of steam systems. They were cleaner, simpler, and increasingly cheaper as production ramped up worldwide. South African railways began phasing out steam in the 1960s. The Class 25s, which had cost a fortune to build, were retired after barely 15 years of service. By 1973, the last one was withdrawn. Most were scrapped. Their condensing tenders, those magnificent engines of thermodynamics, were cut apart for scrap metal. Only one Class 25 survives today. Number 3450 sits in the Outeniqua Transport Museum in George, South Africa. The condensing tender is still attached, though the fans no longer turn, and the cooling elements are caked with decades of dust. Visitors walk past it without understanding what they're looking at. The locomotive that made British engineers cross an ocean to figure out how it worked. The irony is complete. Britain spent the 1950s trying to copy a technology they ultimately decided they didn't need. South Africa built a machine so advanced it became obsolete before its potential was fully realized. The Class 25 was the answer to a question the world stopped asking. How do you run steam locomotives where water doesn't exist? For that brief moment in the Karoo, under skies that stretched to nothing, the Class 25 rewrote the rules. It proved that colonial engineering could surpass imperial standards. It showed that impossible conditions could drive impossible solutions. And it demonstrated that sometimes the most sophisticated answer is the one nobody remembers. The condensing tender sat silent in the museum, a monument to ingenuity that arrived too late and cost too much. Britain never did build their version. They didn't need to. By the time they'd finished studying the Class 25, the age of steam was ending everywhere. But the engineers who made that journey to South Africa carried something back with them that couldn't be measured in thermal efficiency or water savings. The uncomfortable knowledge that the best steam locomotive innovation of the 1950s hadn't come from Derby or Doncaster. It had come from the Karoo, built by engineers who refused to accept that some places were too dry for railways. The Class 25 didn't just haul freight, it hauled British assumptions about who led and who followed in the world of engineering. For once, the teacher became the student, and the lesson, for those paying attention, was that necessity doesn't care about empire or tradition, it only cares about solutions.